So electrochemistry, it can be used to measure just about anything. It's extremely versatile, and there's a lot of different um, types of electroanalytical methods that we can utilize to measure different analytes in different species. And so I have a few of the most common general techniques that are classified within electrochemical measurements here. We have amperometry, coulometry, and potentiometry, and the names sort of give away what their mechanism is. And so amperometry, of course, is relating current to the concentration of some species, typically. Coulometry is relating the amount of charge Q to the amount of a species. Potentiometry relates the cell voltage, or E cell, to the amount of stuff that you have in solution. This chapter is focused just on potentiometry because it's a massive field in and of itself, and it's non-invasive, and it's a simple method to measure lots of different things, simply based on Nernst equation. So you saw at the end of the last video a potentiometric method to measure Kf of an EDTA complexation with mercury. So potentiometry can be used to measure indirectly equilibrium constants, which it often is, so Kf, but also acid dissociation, base association constants. It can be measured to used to measure solubility products, but it's really good at measuring very low concentrations of a product of some concentration. Also, probably the most common potentiometric technique that you all certainly have used in your lives that you just didn't know it was a potentiometric technique was a pH meter, right? pH really means negative log H. How do you measure that? Well, you measure that by having two electrodes in a solution, one of them in a constant potential, one of them not at a constant potential, where H, or hydrogen ion, is part of the redox expression. You write a Nernst equation, and that's going to change. And we'll talk about that at the end of this series of videos. I think I might have shown this image to you at the beginning of sort of the grand pitch of what analytical chemistry is. And the reason I show it here is because all these sensors here, both the invasive ones and the non-invasive ones, these are all different mechanisms by which you can measure glucose in the body. The majority of these mechanisms here that are shown are electrochemical in nature, just because it's so easy to implement in wearable devices. So this method here, this disposable strip, if you are diabetic or know somebody who's diabetic, you've seen these types of devices. They prick your finger, and then there's this little strip here. This little strip is an electrode. It's actually an electrochemical cell, and the blood, it serves as the electrolyte, and it completes the circuit. And it's not potentiometry, but it's amperometry, and it's an electrochemical method, and it's super robust, and it's the industry standard for measuring glucose. Problem is, you got to get blood out of your body, and so there's several other methods, like implementing these on contact lenses. These exist. These are electrochemical, so they do electrochemistry on your tears. Glucose is in your tears. Glucose is easy to oxidize, and so you can grab an electron from glucose and then measure the current. The hard part is not doing the electrochemistry, it's transducing that to some device that can then measure that out. So building a soft contact lens with interdigitated gold electrodes like this has been around for 20 years. The difficult part is miniaturizing the wireless transduction mechanism, but you know, with 5G, etc., these things are now available. Doing it in saliva is no different. That's just doing electrochemistry in your mouth. Doing it inside of the subcutaneous or in the cutaneous level of your body with these little microneedles. This is huge nowadays. Microneedles are all the rage because they don't constitute invasive because you can't feel them, even though they are technically invasive because they're inserting into your skin. They're not inserting all the way necessarily to the blood vessel, which we don't, into the nerve, so we don't feel this as pain. And then you can, of course, do electrochemistry in your sweat. So virtually, you can do electrochemistry anywhere in bodily fluids, which is what we're made out of. This is also how you do neural measurements. So virtually all in vivo measurements, how we understand fluxes of neurochemicals, transmitters, catecholamines, things like dopamine. The reason we know anything about those is because we construct interdigitated electrodes that look like this, but they're much, much smaller than a contact lens, and we insert those into the brain of a living mouse, and then we subject those mice to certain stimuli to elicit neurochemical responses, and we can measure those really, really quickly and very locally near specific neurons or axons, and that's virtually how we know all these things. This is actually part of my research too, not the not the contact lens, but developing rapid in vivo sensors for the separation of catecholamines directly from cerebrospinal fluid and measuring those things amperometrically. Anyway, I'm sort of giving you a bunch of framing here. This picture over here shows you the mechanism by which this thing works. So the blood disposable strip for measuring glucose. This is pretty amazing. The way that these things work is that they actually take glucose oxidase, and they harvest this not from humans but from other animals, unfortunately. They get high concentrations of this, and then they anchor it covalently to an electrode surface. And then when glucose is in the solution, the glucose oxidase will automatically oxidize, that's its name, glucose oxidase, it'll oxidize the glucose into gluconolactone, and then that electron gets shuttled inside the enzyme to the electrode itself. And sometimes these things will measure the current directly, amperometrically. The other way to do this is colorimetrically. So the electrode, or the electron from the glucose oxidase goes through this thing called Prussian blue, which is a solid state redox couple, meaning it's completely insolid, it's not aqueous. And when you pop an electron into Prussian blue, it turns colors. And so you get this solid state sensor where the color changes. The problem with this is it's binary, so it just goes from blue to not blue. But that can be good enough if you're looking for a binary sensor that just says your blood level or your glucose level in your blood is below a certain level. Then these things get calibrated in such a way. So anyway, this is an introduction to using voltage or cell potential to measure the concentration of an analyte in complex matrices.